Okay, so hi folks, and welcome to lecture 20 of ECE 3311, Principles of Communication Systems. Today, what we're going to be doing is we're going to be doing frequency shift keying, all right? So what frequency shift keying is all about, or FSK, okay, so that's a shorthand for this, is the idea of being able to communicate information, okay, every t seconds, so every symbol period, based on just the frequency information contained within our modulated signal, right? So what we're going to do is we're going to look a little bit about, again, our sort of like basic waveform and how that information gets modulated into that signal. And then afterwards, what we're going to do is we're going to look a little bit at like the receiver structure of how that's implemented, all right? So first of all, again, let's go back to sort of the basic principles behind what we are doing here in terms of our communication systems. All right. So what we've got, okay, is sort of again, the general expression. All right. So what we got is S of t. Okay, that's our passband signal. Is equal to the real of g of m of t, e to the j 2 pi fc of t. So fc, okay, that's our carrier frequency. Okay, this here, that's our baseband signal, and it does a mapping from our message signal m of t to that signal, right? Now, one thing again, because we're dealing with digital modulation, digital transmission, is that information, okay? This mapping occurs from bits, binary information, to the baseband waveform, the baseband signal, every TS or symbol period, okay? So this is very important. So in this case, all right, with respect to something like ASK, amplitude shift keying, what did we see? We saw that the information was contained within the amplitude value of the g of m of t, right? So amplitude contained the binary information, the binary info. We looked at PSK, phase shift keying. And in this case, the phase info contained sort of like contained the info, the binary info, right? The binary message. Okay. So now what we're looking at is FSK, the frequency itself, frequency shift keying. And, you know, frequency contains binary info. And if we drew this, okay, we saw a little bit about what happened, right? With the ASK sense, what we saw before, over time, every TS seconds, and so on, what we saw is, first of all, there's an envelope. Something like that. And of course, we had a matching one. Yikes. okay? And our carrier fit there, right? This cosine wave, right? And the information was contained in the envelope of that carrier, right? My badly drawn carrier. Then for phase shift keying, amplitude stayed the same, okay? Over time. So every TS seconds, what we had instead was it's a constant sinusoid or cosinusoid, but what happened was the phase of that sinusoid, okay, relative to some reference, was changing, and that change, the amount of phase change, is relevant to the type of information that's contained within TS seconds. Okay, so like let's say the easiest one was we looked at 0 or 180 degrees, because the 90 degrees and 270 degrees is actually kind of very painful to draw, right? So I'm going to be slightly lazy here, but it also makes the point a lot more clear. So let me bring that up. There we go. All right, so let's say this was 0 degrees. That corresponds to binary 1. And let's say that's a binary 1. And binary 0 is 180. So what this would look like. So remember, no information contained within the amplitude. And then what happens is, oh, it's 180 degrees phase shift. Everything is in opposite mode, right? Up, 180 degrees phase shift. Here, there's no, because we're going from 1 to 1, it's still the same phase. But here, 180 degrees phase shift. And here, there's no change from it's 0 to binary 0 to binary 0. They're the same phase. So we keep on. There we go. So here in this case, the information is completely contained, whether there's a phase shift or not, right? Boop, right. So now we're going to look at a different case, which I'm just going to like draw kind of like, you know, for instance, very naively. Let's say 0, TS, 2TS, 3TS, 4TS, 5TS. And again, let's say amplitude and phase are the same. Okay, all else things being the same, but let's suppose that a binary 1 is represented mapping-wise by frequency, let's say mu. What type of frequency should we be using? Let's say we have it's like, let's say frequency F1. And if it's a binary 0, let's say it's 2F1, right? So here, so this is going to be somewhat easy to draw. So let's say I have this, and then here, no phase change, but I double the frequency. What is this thing going to look like? Oh boy, 1, 2, 3, 4. Okay, let's do this. 1, 2, 3, 4. Then, okay, now I'm going back to 1, halve the frequency. 1, 2, right? Still 1, 1, 2. Oh, I hit a 0. Oh boy. So it's going to be 1. Oh, thank goodness. Okay, let me draw this better. 1, 2, 3, 4. And then again, 1, 2, 3, 4. So what happens is here we have double the frequency during that TS seconds, double the frequency here, double the frequency here. So we have a decoder, right? We have a receiver that says, ah, that must be 0 during that. And this is like binary FSK. And then on the other hand, we have a 1 and it's half that frequency. So when we look at those, okay, this segment, this segment, this segment, we decode it and saying, ah, okay, that's a binary 1 that's been transmitted. So that's kind of like the layperson's viewpoint of how FSK works. All the information is contained in terms of what that frequency of that sinusoidal carrier looks like. All right. So that's very important. So let's dig in. There we go. I just want to bring this up. Yep. So now let's go back to the slides. All right. So again, general expression should be no surprise. I think we've been seeing this like a lot of times. And then what ends up happening is if we look at I'm sorry. I'm getting like distracted here. There we go. So now if we go to the next slides here, this is what we call the discontinuous FSK, right? So what happens is we switch between 2 oscillators. And that's what happens is it's kind of it's simple, right? So the way, like, you know, symbolically we would draw something like this is like the following. Hopefully not like that. But what happened is something that looks like the following. So you would have some sort of multiplexer, right? And you would basically have one of 2, you know, sort of oscillators, each one with a different frequency, right? And what would happen is you would implement this like the following. Like you would either, so if it's discontinuous, you would have constant amplitude, you would have cosine, and then it would be 2 pi f1 of t, and then it would have some phase, right? And otherwise, and let's say the frequency here, f1, this corresponds to a binary 1. And then here, you would have f2, so cosine 2 pi f2 of t, and then you would have some phase. Again, phase, it's not the phase information we care about, it's just the frequency information. And that would be a binary 0. And what would happen is this multiplexer, right, mux. So every TS seconds, what would happen is that data stream, right? So it'd be 1, 0, 1, 1, 0, 0, right? So every TS seconds would select which frequency it would be, and would just stitch them together and spit it out. Now, the discontiguous or discontinuous FSK, you know, again, it would have the same amplitude, but the only thing you're looking at is like a kind of like a very kind of like rough type of signal that's been put together. So they might not even have nice sort of like, oh, what the heck would it be? Sort of nice transitions between 1 and 0, right? Between the different waveforms. So what you would have is something that looks like this. So, you know, you might potentially have, okay, here's your signal. And then all of a sudden, it would be very sharp, abrasive transition, even in terms of the signal, because what the heck, it doesn't matter. All you're doing is observing the frequency, and you have, oh, now you go back to this, And it's not really all that great, right? So let's say that was a 1, that was a 0, that was a 1. So the discontinuous FSK does not have that nice transition, lacks smooth transition from one, okay, waveform representation to another. It literally is use this cosine or use that cosine. Maybe if you chose the parameters of f1, f2, and theta 1 and theta 2, you can get that kind of like, like you don't have discontinuities, or at least not as severe, but you could do better. And so there's another type of FSK. Okay, so what you would do, okay, so let's switch to the other one. What you would do is you'd have something like this. You would have the continuous FSK. Okay, so the way it would work is something along the lines of the following. What you would have is your message signal would kick in. And again, we saw this before with FM modulation, right? So you have this beautiful, integral from minus infinity to t, your current time instant, okay? And that integral of your message signal, and then the integral of that message signal would be multiplied by df, some sort of constant, and that would be part of the argument with your cosine and would dictate what the frequency would look like for that cosine function, right? So what it would look like, okay, yeah, is there would be a transition. So when I think of integral, what do I think of? I think of sum, right? I think of some sort of sum. And so what it would be in particular is something like this. So what would happen is the way continuous FSK would work is, let's say this is a binary 1, that's a binary 0, that's a binary 1, that's a binary 1, that's a binary 0, that's a binary 0. And this is time. What would happen is the following. So let's say, okay, I got this frequency here. Oh, but now I need to go to, let's say, this crazy frequency. Okay, so the way this would work is that it would go from F1 to F2, but it's going to like transition. It's going to like increase the frequency continuously, right? So it's going to look like this, if I can draw this better, okay? So it's going to speed up and speed up and speed up and then connect. So it's going to go from an F1 frequency to an F2 frequency. And then here at 0, it says, oh, but I'm going to go back to that slow frequency that F1 is. And so I'm going to slow down to now back to F1. And then, okay, and still F1. So I keep on going at the slow frequency. But now I see an F2 and I speed up and do that. So this is a much more graceful way of doing FSK. Instead of like hard, abrupt, boom, your frequency 1, boom, your frequency 2, boom, your frequency 1. Rather than doing something like that, it's sort of this nice continuum change of frequencies, right? So like from F1, you continue being F1. Now you transition to F2, so you speed up, and then you continue being F2. There's no transition. So it's a lot more graceful, right? And that's achieved by that phase term that we have with FM, where we've got df integrate from minus infinity to t. So that's the important factor, is that integration. So instead of instantaneous, it smooths things out. It takes all the past values and allows for that gradual transition to that new frequency value. So that's m of t. Yeah, got to be careful. It's not t. The integrand here, okay, so the variable for integration is tau or lambda or whatever you want to choose. T is the current time instant here, right? Okay, cool beans. So how do we represent that? How do we represent that FSK? So the way it would work, okay, is the following. So let's jump. There's probably a good. There was a good example that I wanted to do over here. All right, but the way it would work, all right, is the following. Okay, so you would have this. So first of all, you need to have some sort of translation of that message signal. Remember, it's binary values, right? So those binary values have to go into need to be translated into that M of t waveform, and then that M of t waveform is what allows you to transition to this phase value that ultimately goes into your S of t, right? So okay, so okay. So let's find an example where this is the case, right? So where is it? So there in your book, there's a kind of a few kind of crazy examples of this type of waveform that you can use, right? So for instance, if you look at okay, so in the course textbook, okay, so this is figure 5-25. Okay, you're given a few examples of how you can represent this type of this M of t message, right? So M of t. So first of all, so a couple of waveforms that come up, right, is the following. So suppose this is M of t, right? And what you got is a nice, suppose you have something like this. And you say, okay, neat. So let's say this represents a binary 0. Yeah, sorry, binary 1, binary 0, binary 1, binary 0, binary 1, binary 0, and so on and so forth, okay? So this guy here, the value is what? +1. Let's say the value here is -1. So what we would need to do, this is actually perfect because it highlights, okay, how that integral function will work, right? So what would happen is if I were to integrate from -infinity to t of M of, let's say, lambda, tau, sigma, whatever you want, the dummy variable here, okay? What this would look like is you would be integrating, right? You would be integrating this function, right? So what would this look like? If I were to take this, right? So let's say I take this function. What would it look like? So first of all, we would have here TB. So remember, if it's binary, TB is equal to TS, the symbol period. Okay. So what this would look like is what is this sort of like? This would be an accumulator, right? So the way this would look like, so if we look at one accumulation, what this would look like is something like the following. Let me see, and that's 0. So if we took one, let's suppose we had something like this, like a cycle. Like that. What would this accumulator look like? Well, so suppose we had an initial condition, okay? and the accumulator said, all right, I have a value here, okay? And I'm gonna sort of I'm gonna give away what the minimum value of this integral is, which is going to be equal to, right, minus 2 pi, right, delta f t naught divided by 4, right? And so you might say, okay, what the heck is delta f? So delta f, okay, delta f is going to be equal to df, oh, that's it, divided by 2 pi. All right, cool beans. So in some ways, what the delta, this df represents is the slope. All right. Now, the other thing, t naught. So here, well, we'll get to t naught. What is t naught? T naught is equal to 2tb. Okay. So think of it this way. It's a stretch across. So this is 1 TB. And that's another TB. So let's say this entire cycle. All right, cool. So suppose we start there. What does this accumulator do? Well, what this accumulator does, what the integral does, this integral expression, so let's say minus infinity until t, okay? So what happens is as t, little t, progresses, what does an integral do? Essentially, what it does is it takes the area underneath the curve, right? So let's say t is equal to this value here. What does it do? It's going to be the value of the area there. Now, if t is over to here, what do we get? That area and that area. So what it does is it progressively gets a bigger and bigger positive area until here, right? Until we traverse TB, right? This expression just accumulates, and adds to this negative value here, right? So what does this look like? So as we're progressively adding, it's going to look like this, right? Now, all of a sudden, now we have negative values of area. And what ends up happening is now those negative areas begin to chip away at the positive gains made by this positive thing here, this guy. So now we go back. So it's actually pretty cool. So what at the end of the day, what we have is our phase term, right? This thing here, theta t, is going to be equal to this ramp up, ramp down, ramp up, ramp down, ramp up. If we do this, okay, and if these values are continuously alternating, right? So that's what we get here for in figure shucks. If we look at figure from the course textbook 5-25, what we get is this like sort of ramping function, which makes sense, okay? And what ends up happening is with that ramping function, we get which intuitively makes sense. As we take the integral of whatever pulse we have, in this case, it's a it's a polar 1 or 0, 1 or minus 1, representing the binary 1 or 0. Okay, we get this triangular function, and that triangular function is gets contributed to your frequency value. Okay, for that cosine wave. So that's what we get. All right. So now that we have that, okay, So first of all, like there are going to be several other things that we're going to be looking at here. So this guy, what happens is at the end of the day, if you look at it, it's actually kind of interesting because we actually, if we go into more of the mathematical analysis of how this works, right, in terms of like the FSK, it actually gets a little bit more complicated. So in the case of FSK, as opposed to phase shift keying, as opposed to amplitude shift keying, what FSK looks like, okay, if we have something like this theta, this m of t function, and then translating it into a theta t, what we need to do is we need to use Fourier series. Oh boy, yeah. So this is going to be fun. And so what ends up happening with the Fourier series representation is that we know what the expression looks like, but we need to figure out what the Fourier series coefficient is, right? If we have something periodic like that rectangular representation for m of t, right? Okay, because that way we can actually figure out what spectrally this looks like. Okay, all right. So that's a little bit about what FSK is about. And again, it's a little bit trickier because ultimately what you'll get in terms of your FSK spectrum. So if we work this out, so let's actually work this out. So FSK spectrum. It actually gets a little bit more complicated, right? Sad but true. So what ends up happening is, okay, let's look at this thing. So we have that representation, right? So we have now, delta f, and that's going to be equal to df over 2 pi. Okay, great. And then on top of it, what else do we have? T naught equals 2 TB. So this is obviously binary FSK. What else is there? Okay. So what we need to figure out is something called the modulation index, right? So modulation index in this case, the modulation index is defined by h, okay, and is equal to 2 delta theta, the change in the phase, divided by pi, which is equal to, lo and behold, delta f t naught. So the change over 2, so think of it this way, the change over two symbol periods, right? Which in this case, because it's binary FSK, two bit periods. What we want to find out is the change in the frequency, right? And this is equal to, okay, 2 delta f, right? So that's the slope, or divided by r, which is the data rate, the bit rate, okay, r. Not the symbol, well, symbol rate, bit rate, it's the same thing because, again, it's binary FSK. And just FYI, because we made this jump, because r is equal to 1 over TB. Okay, awesome sauce. So now what happens is we have this thing, right? H over delta F. We can also define it by B, okay? And this is equal to beta F. This is going to be important because what's going to happen is this will define the FSK modulation scheme. Is actually a little bit weird looking. So it's going to be a lot of deltas. I'll show you in a second. But what happens is, okay, this is going to be equal to, okay, so this beta F, we're going to, this is going to be very important. So this guy here, that's the bandwidth, okay, of m of t. Okay. And this is defined by b equals 1 over t naught, right? Again, no surprise. So because it has that periodic nature, we cannot use Fourier transforms. Okay, we have to instead use Fourier series. Okay, therefore, my g of t, okay, my g of t, this is important. What happens is it's going to be represented, okay, by a continuum of these Fourier series coefficients, and it's going to be e to the j m omega naught t. Okay, that's going to be important. Oh, sorry, not m, n. Okay. So what happens is, again, that guy, oh, well, this is going to be equal to, so remember, f naught is equal to what? 1 over t naught, and that's going to be equal to r over 2. Okay. So now if we look at what Cn is equal to, Cn is going to be equal to AC, okay, that's fine. Because remember, again, we're trying to represent this guy, which is the complex baseband signal, okay, which is a translation of that message signal m of t to the complex baseband signal that's going to be then applied to the carrier frequency, right, the modulation process to FC, okay, and then we'll apply the real operator on top of it. What we got is we take the Fourier transform, basically, of one period. Okay, so we got that. All right. So now we're integrating with respect to t. So this gets a little messy. So what ends up happening at the end of the day, if you do the integration, because what you'll do is you would want to take, okay, so here's the trick. So the first thing you would want to do is group everything together. Nope. You would want to group everything together into one common base. Yeah. So what you would want to do is you would want to, so that's the first step, is you take everything into one common base. And then what you would also want to do is you want to start dividing things up. So, okay, let's do this. I'm getting my indices messed up. So the first thing you would want to do is you would have that integral expression. So, okay, great. But what you would do, okay, so you would have j theta t minus n omega naught t, correct? Yes. Then what you then do, the next step, is you would start splitting things up. So how so? So first of all, what I would do is I would cut this up into the following. So limits of integration, t naught over 4 to t minus t naught over 4 to t naught over 4. Okay, great, awesome sauce. And I would also start replacing stuff. So I would say, okay, delta omega t, okay, minus n t naught, yep, that's it, t. And then I would also take these limits of integration, then t naught over 4. Okay, and you might say, what the heck did I do? Well, because remember, periodic, I shift it by t naught over 4 and break this up into two integrals. Okay, And there's a reason why I'm going to do it. I'll show you in a second. Okay. So then here, delta. Okay. Here's my shift. Okay. Now, what I do is I do delta omega. This guy here is equal to this. Okay. So that's where I got this from. So it's like, huh? Where did I get? Okay. Now that's the delta F that I defined before. Then this is equal to the modulation index, delta naught. All right. And so if you plug this in, okay, and you do the integration, what you'll get at the end of the day, okay, with Euler's relationship and all, is you're actually going to get two sinc functions. You're going to get this. That's why I have like side by side. So what you're going to get is sine pi over 2 h minus n. Come on, there we go. And then pi over 2 h minus n. And this is the funny one. So this has alternating 1 minus 1 depending on what the value of n is. Ha! Oh my God. So this is actually really, really cool. So this is going to be that. Okay. That's actually pretty powerful stuff. So that's my other sinc function. All right. So this is actually really, really important. So now I have that. And remember that h is equal to 2 delta f divided by r. Okay. And so now if I draw this out, okay, so if I were to draw this thing, what it's going to look like is it's going to be a lot of fun. The spectrum actually for FSK, yeah, so FSK spectrum. Yeah, let's not put that vertical thingy there. What's going to look like? So let's say that's f of c. Okay, great. What you're going to have at the end of the day is you're going to have these fellas here. So that's going to be F1. Nope, sorry, F2, F1. And then what you're also going to get are these other deltas as well, right? And just progressively looks like that. So what ends up happening is you're going to have like something that looks like this, right? Of course, your F1 and F2, which is what you're trying to modulate with, are embedded in all of these things. So you have a receiver that picks out one or the other, right? So so this here, this example, right? This is from figure, let's see. (5-26) in your course textbook, specifically figure A. Right, so this is a spectrum where you got F2 is equal to hertz, and F1 is equal to hertz. So what you got, okay, are these sort of spectral lines, right? But the ones to keep a close eye on, where the information is stored about what symbol it is or anything like that. Like, how does it look like? The actual representation at the different, like, is it an F1 that has been transmitted sign-wise, or is it an F2? Are these two here? And it really varies, right? So carrier frequency is always going to be in the middle, right? And then you have all these sort of byproduct deltas that kind of spawn off of it as well. And so if you do the actual like sort of mathematical analysis, so you might say, well, where does that come from? Well, that comes from, okay, that actually comes from over here when we do the G of t and we have all these things, right? So that's where we get this FM. So it looks relatively complicated in order to actually like spectrally what the heck this thing looks like, right? All right. So let's go back here. So first I'm going to save. Thank goodness. All right. All right. So, okay. So coherent detection versus non-coherent detection. So the way this works, okay, with the FSK, obviously you're going to have to know what the frequencies are. Is like actually the way this would work. Actually, let's see. Okay. So first of all, again, depends on so. Okay. So again, what we need is something that in case, like for instance, if we had binary FSK, would be able to extract out whether it's F1 or F2 that has been communicated in the transmission, right? So what we need is one of two possible receiver structures where one obviously is going to be very sensitive in terms of the timing of what we get in terms of the received signal in order to extract out one of those two frequencies. And the other one is irrelevant of what the timing is. As time goes along, it will give us what the F will be, okay? Whether it's F1 or F2. Oh, shucks. Okay, so what we'll do is, I think we're going to stop there. But at the beginning of the next lecture, tomorrow's lecture, lecture 21, I'll finish off this example in terms of coherent versus non-coherent detection for BFSK. So what did we learn today? Okay. Well, obviously a lot of mathematics in terms of like, how do we get the spectral lines of an FSA signal? It's relatively complex. So to see this on like a class test or something, probability is a little bit lower because it's just a lot of mathematics and very difficult to plot once you have it. But however, you should be familiar with how, first of all, the creation, not so much with respect to the discontiguous or discontinuous FSK, but more importantly, the creation of the continuous FSK is done, right? So you should be able to see how you go from one frequency to another in sort of a seamless transition without any sort of abrupt changes between two different symbols at the symbol period boundary, right? So that is a major walk away from this lecture. So you definitely should be aware of that. You should also be aware of the fact that there are two different types of FSK out there, that there's not just, there should not just be like, oh, FSK is FSK. No, there's a graceful way, and then there's kind of more abrupt way of doing it. And and of course, that the spectrum looks kind of rather complicated. You should be able to understand what the derivation, where it comes from, in order to do it from memory or on a class test. That's a little bit more difficult to pull off unless it's like a very simplified version. But again, less likely of that happening on the class test. And continuing in tomorrow's lecture, we'll look at how to demodulate an FSK signal. So with that, that concludes lecture 20 of ECE 3311, Principles of Communication Systems.